Hello, welcome back. The title of this lesson is called Radians, Arc Length, and Sector Area. This is part one. Kind of a weird sounding title. We're going to cover a few different items which all kind of fit together in this lesson. So in the beginning, I'm going to write down the equations for the arc length for part of a circle, along with the sector area. I'm going to write them down and just give them to you. And then we're going to derive them, because I want you to know where they come from, and then we're going to use them. So we're going to do all of those in this lesson. So let's just write down one of the more important geometric formulas that we have, which we also use quite a bit in physics for a lot of practical reasons. So let me first draw some sort of circle, and what I'm going to do is superimpose it on an XY plane. So this is pretty common. So you can say, this is X, this is Y. Now my circles, they're not going to be great, all right? So just kind of forgive me on that. So this is my best attempt at a freehand circle. It's not that great. It's lopsided, it's off center, but you get the idea. And what we're going to basically say is I'm going to put a ray here, kind of cutting through right here. And so there's an angle here, which we call theta. And what I'm going to do is I'm going to tell you that this arc length right here, this length as traveled across the boundary of the circle, we're going to call that S, which is what we call the arc length. All right, and we have a radius here as well, which I need to draw in the picture. So the radius of this circle right here is the radius from the origin all the way to the boundary there. And we don't really need the arrow to extend past, so I guess I can just erase that. So we have a radius there. So what we have here is an equation called the arc length. Right? The arc length. Again, we use it a lot in geometry, use it a lot in physics. So the arc length S is equal to the radius R multiplied by theta, right? But the important thing is that theta here, this is measured in radians, right? So what we basically figured out here is if you were to measure the distance along the edge of the circle from this point here all the way up to where the ray stops, when I say the arc length, that means it's the curved distance along the boundary of the circle. You know, we all know how to find the entire circumference of the circle all the way around. This is just a portion of the circumference from this point where it touches the x-axis up until where the boundary goes. And this, of course, this kind of like distance in terms of an angle, we call it theta. You can measure theta in degrees, you can measure theta in radians, okay? So if you keep theta in the radian unit of measure, and you know that the angle in radians, and you multiply it by the radius r, then what you're going to get is the arc length distance here. Now, when you see an equation like this, it doesn't make any physical, in my opinion, it doesn't have any physical meaning. You don't really know where it comes from. So what we're going to do is leave this on the board, and then I'm going to show you another equation that kind of goes hand in hand with it, and then we're going to derive both of them. So you are going to understand where they come from, but for right now, just trust me that the curved distance here is equal to r times theta. And that is something we use a lot in physics and in geometry. So let's move along and write down the next equation or the next formula that we need here. What I'm going to do is draw another circle. And again, I'm not going to be able to draw a good circle, so let me draw a circle like this. Okay, that's not too bad. A little flat, a little like a pumpkin, but you get the idea. All right, so what we're going to do, this is going to be the center of the circle. And what I will do is kind of draw a line out to the edge and then a line out to this edge right here. Again, this is the center of the circle here. And it has a radius r. And there is some theta radians here, like this, theta radians. Now what I'm going to do is say, what if I want to find the area of the shaded region right here? Area of the sector. Whoops. So I'll say A equals the area of a sector. And what I mean by that is this entire shaded region, which I'm probably going to make it difficult to read by doing all the shading like this. So you see, these two equations deal with just portions of a circle. We already know how to find the area of the entire circle. We've been doing that since 4th grade. We already know how to find the circumference of a circle all the way around. Again, we've been doing that since 4th grade. What we're doing now is finding a portion of the circle. What is the area of this wedge, this pie-shaped wedge, which has a radius of r in whatever units you're talking about, and some angle here, theta? What is the area of that shaded region? And what is the distance along this curved path, again, marked by the boundary right here. So what we can do is write down the area of a sector. The way we say it is area of the sector of a circle, right? And there's actually two different equations that you can just use interchangeably, whichever one you want to use. You can say that the area is 1/2 times r squared theta. You can also say that the area is 1/2 times r times s, right? Again, when I put theta here, this is in radians. That's very important. Don't put theta in degrees. Degrees is a little bit of a, we use it a lot, but it's a little bit of a hokey measurement for an angle. The more natural units of measuring angle is always in radians. So if I know that I have a pie-shaped wedge of the circle where the boundary of it is measured by the 2 radii r, and there's some angle in whatever, 3 radians or 2 radians or 1 radian or whatever it is, then either 1/2 r squared theta will give me the area in square millimeters or whatever it is, or 1/2 r times s. Either one will work. So what we want to do, I have these up here and we're going to use them, but I want to derive them. I want you to know where they come from. They're also very easy to understand how to derive them. Once we get done with the derivations, we'll do a couple of problems to show you how to use them. Also very, very easy to use. All right, now the first one we're going to derive is the arc length. It's actually a little easier, I think. So let's go back and talk about the unit circle, all right? So let's go and draw a unit circle. How do we draw a unit circle? Well, first of all, we want to draw an XY coordinate axis, and we put a circle right on top of it, which this is not a perfect circle, but you get the idea. And a unit circle means it has a radius of 1. So I can put a 1 right here, 1 right here. This is -1 over here, and this is -1 down here. So the radius of the circle is 1. 1 what? What are we talking about? Well, it could be centimeters, millimeters, meters. It just depends on what what distance unit you're working in. Let's call it meters. So this is 1 meter, 1 meter, 1 meter, 1 meter, like this. All right. Now, what we need to do is remember or recognize what we have already learned about radians. All right, so if we draw a little dotted line right here and we say that there's some angle radians here, what does this actually mean? And we have talked about this before, but this is a little bit of a refresher and to refresh your memory on what a radian is. Because a lot of students say, well, we already have degree measures. We know there's 360 degrees in a circle, so why do we have radians anyway? And I've been telling you, even in this lesson, that radians are a more natural unit of angles. We need to review why radians are a more natural unit of angles. It's important for its own reasons, but also it's important to do this derivation, okay? So when we have a unit circle, which means a circle with radius 1, and if we, when you think about it, 360 degrees in a circle, there's historical reasons, you can look them up as to why there's 360 degrees in a circle. I'm not trying to argue that. But I'm saying, wouldn't it be a more natural way to measure angles if we just draw a circle and we just say, okay, this is some angle, this is an angle bigger than that, this is an angle bigger, 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 and when it comes all the way back to where it starts, it seems to start over again. So what we'll do is we will divide up the circle into an equal number of units, and of course you can use degrees, but let's talk about what would make a little more sense. What if, instead of degrees, what we do is we invent a new measure called a radian, and the radian is just the distance along the edge of the circle. Think about that. I'm going to say it one more time. The radian measure for angles is just the distance that you walk along the edge of a unit circle as you sweep it out. So if you have an angle drawn here, what does the radian measure? Well, you get a ruler or a curved ruler, and you measure the curved distance from here to here. And that is going to be the number of radians, okay? Now, of course, we have a unit circle here, so this definition of the radian is only true if you're dealing with a unit circle. So for instance, if this were 1 meter, 1 meter, 1 meter, 1 meter, and you measured some distance here, like, I don't know, 0.1 of a meter, okay, and there, then that would be 0.1 radians. And if you go all the way around like this, then you have a more and more distance than you're always starting from the x-axis. So here is a quarter of the circle, here is half of the circle, and here's 3/4 of the circle, and here's the full circle. And the distance that you're walking around the boundary is what we call the radian measure. But again, only when we have a unit circle. Now let's see if this makes any sense, because you might not remember this, or maybe you've never learned this. And so it's like, okay, Well, let's just say, let's pretend that theta is equal to 2 pi radians. You already know that 2 pi radians means you go all the way around the circle back to the starting point. So let's say that you start from here and you go 2 pi radians, which means you should go all the way back, because we know 2 pi radians means you go all the way back to the beginning, right? What would the distance be? Because this is a circle, we know how to calculate the circumference of a circle. What is the circumference of a circle all the way around? Well, the circumference of a circle is 2 pi r. But the radius, we already know the radius of the circle is just 1. So what we know is it's just 2 pi times a radius of 1. So the circumference, when we travel all the way around the circle, is just 2 pi, right? So what I'm trying to tell you is that I'm trying to tell you that the radian measure is the distance that you walk all the way around when we have a unit circle. And then I'm proving to you and saying if the radius actually is 1, and you know how to find the distance all the way around, it works out to be 2 pi meters or whatever it is. Well, that's all the way around. And the distance all the way around this is proving to you that it's 2 pi radians all the way around. Because if you take a radius of 1, and then we know that there's 2 pi distance units all the way around, we say that theta is equal to 2 pi in this case, and so that checks out. All right? So in other words, what we have basically written down indirectly is that there are 2 pi radians in 1 rev of the circle, right? In 1 rev of the circle. All right? And specifically, when you look at the definition of a radian, first of all, you talk about that unit circle. That unit circle is so important for so many different reasons, right? It's important for trigonometry. It's important for this, which doesn't really have anything to do with sine and cosine, but you see the relevance of it. Instead of just saying arbitrarily that a circle can be divided into 360 units that we call degrees, instead of that, let's just say, okay, what if we have a unit circle and we just define the angle to be how far we walk along the edge of the circle? Then if the circle had a radius of 1, because we know that there's always 2 pi r distance units all the way around, if the radius is 1, there's 2 pi distance units all the way around. We're just gonna invent a new measurement called a radian, and we're gonna say there's 2 pi radians all the way around. So this is really the reason why there's 2 pi radians all around. There's pi radians up to here because that's half of that, and there's pi over 2 radians only going a quarter of the way around the circle. Okay, so we figured out, based on a unit circle, how this works. Now we need to travel back to what we already said. We said that the arc length here is the arc length s, which is the distance along the boundary of the circle, is equal to r times theta. So we say arc length, right? S is equal to r times theta. Now let's ask ourselves, does this make sense? Does this equation, does it match what we already know about the circumference of a circle and the definition of a radian and all that stuff? So then we ask ourselves, okay, what if the radius of the circle becomes 1, right? Then 1 goes in here, and then the arc length is just going to be equal to however many radians we walk around the outside, okay? And then we already said if theta becomes 2 pi radians, then the arc length, which is all the way around the circle, is going to be 2 pi, which is exactly the same thing as the circumference, which is 2 pi r. And when the radius is 1, then the circumference is 2 pi. So you see, it all makes sense. So the arc length is a portion of the circumference, essentially. And if you take as a check that when the radius is 1 and you walk all the way around, you figure out that the arc length is telling you the distance is 2 pi, which is exactly what the circumference of a circle formula tells you. Let's check one more. Let's say if, let's check if the radius is equal to 2, and let's go all the way around the circle 2 pi radians. Then this equation, s is equal to r theta, is telling us we put an r of 2 in there, and a theta of 2 pi. Then it tells me the distance all the way around a circle with a radius of 2 going all the way around 2 pi radians is just equal to 4 pi distance units. Is that correct? Well, we check it. The circumference of any circle is 2 pi r, which is 2 pi times r, but r is 2 in this case, right? So 2, and so you get 4 pi. So you get exactly the same thing. So I guess what I'm trying to tell you by kind of analogy, it's not a rigorous proof, but basically what I'm trying to tell you is you already know the circumference of any circle is 2 times pi times r. That 2 pi Spoiler alert, it comes from the fact that there's 2 pi radians in the circle. Because we know, now you know anyway, that the arc length of any circle is r times theta, right? And so if you just leave r there, and if you decide you're going to go all the way around the circle and find its circumference, you put 2 pi in there. 2 pi r is the arc length all the way around the circle. So this arc length formula, this is a very long-winded way of saying it's just kind of like a special case of the circumference formula that you've been using forever. It's just now this thing allows me to put a different amount of radians in. Instead of going all the way around 2 pi every time, I can put however many number of radians I want. I can put pi over 2. And that would tell me the distance up till the pi over 2 mark here. I could put pi in there, which would just give me the half of the circumference of the circle, and so on. But you can see that every time we've checked it against the circumference of a circle, we get the same answer. So this is the arc length formula, r times theta. So now what we want to do is turn our attention to the area of a sector of a circle, which is this guy, and derive this. What we want to do is basically say, all right, look at this picture. We have a wedge, which is a pi-shaped wedge where it's a radius r bounded here, and it's got some angle theta in radians. And we're going to use the variable a to be the area of a sector of this sector, the shaded area here. So what we're going to do is use proportions. Right? What we're going to do is we're going to use proportions. What we're going to do is we're going to say, all right, the area of this sector of a circle, which is A, so the area of this shaded region, compared to the area of the entire circle as a ratio is what? So that's just A, which we're trying to find, A. What is the area of the entire circle? Is pi r squared. And we're going to say that that's equal to, and so instead of comparing areas, we're going to say this angle theta can be compared to going all the way around. So this area theta is just going around this same portion of the circle compared to how many radians are in the entire circle? 2 pi radians. So make sure before we go any farther that you understand what this is saying. This is just like any proportion problem. It's like 3 is equal is in ratio with 4 is the same ratio as 6 to 7. If you're talking about the ratio of boys to girls in a room, or if you're talking about the ratio of voters or whatever, you're taking 2 different ratios and you're setting them equal because you're saying those ratios are the same. What this is saying is the ratio of the area of this little sector compared to the area of the entire circle is the same ratio as this little bitty angle as compared to the angle going all the way around. Little bitty angle to the angle all the way around. That's why they're equal, because we're saying that these ratios are the same. Whatever this area is, as compared to the area of the whole thing, is the same ratio as this angle is compared to the angle going all the way around. It's the equivalence of 2 ratios, which we call a proportion. Now what we're trying to do is derive what the area of this sector is. So we're trying to solve for A. That's what we're trying to do. So what we're going to do then is we're going to say A is going to be equal to this whole thing, theta over 2 pi, and then we're going to multiply by pi r squared. So pi r squared. We're going to multiply by pi r squared. Notice now that we have a pi on the top and a pi on the bottom, so we can get rid of that. And then we can say that A is going to be equal to theta. Well, let's rewrite it. Let's rewrite it. This 2 on the bottom, we're going to just pull out as a 1/2. And then the r squared, I'm going to write it next door as r squared, and I'm going to write it as theta. So all I've done is rearrange the 1/2, then the r squared, then the theta. And this is exactly one of the formulas that I already wrote down there. So that is the first one. Now, we can go a little further. So let's go up over here. But we already know from previously that S is equal to r theta. The arc length is equal to r times theta. So we already know that if we can solve for theta, theta is equal to S over r. This is just coming from the arc length formula. So what we'll do is we'll just take it and we'll stick it into this location. So we know that A is 1/2 r squared theta. And then what we'll do is we'll just take this and we'll put it in this position here just to get a different formula, because sometimes you're given different unknowns. So r squared, and then theta is S over r, like this. Now when we have it like this, we have an r on the top and an r on the bottom. We'll cancel this one with one of these, and then we will say that A is 1/2 r times S. The r from here and the S from here. This is the other equation. So the area of a sector of a circle can be calculated two ways. Sometimes you're given the radius and the angle that defines the pi wedge, and sometimes you're given the radius and the amount of the arc length along the edge of the circle, which also is indirectly related to the angle. So some problems you might use either one. So I wanted to, in the beginning, just give you the equations so you can start using them and start kind of letting them roll around the back of your mind, but I also wanted to derive them for you. So we derive both of them now. Let's now take some time to use them. And they're not difficult to use. The only real gotcha is you have to make sure every time you deal with theta, you always put radians in. This is something you have to get used to anyway, because when you get into physics and calculus, you never use degrees. I shouldn't say never, because in electrical engineering, we use degrees a lot for certain situations. I'll get to, you can watch those lessons later. But for most pure math, we're using radians because it's a much more natural system of units. And so when we're using theta here, it's going to always be in radians. Your radius is going to be in whatever distance unit you're working in, like meters or centimeters. And then the area will come out to be in square centimeters or square meters related to whatever distance unit you have here. All right, so let's jump into our first problem. These are going to be pretty quick. What I'm going to do is I'm going to give you a diagram, and in the back of your mind, I want us to each have this diagram kind of like in the back of our mind. So we're going to define like a little sector wedge right here. It's got some angle here, it's got some radius, and it's got some arc length, and this whole thing here is got some area, A. So S is the arc length defined by this little pie-shaped boundary edge, just from here to here. Theta is the angle in radians. R is the distance from the center to the edge. And area is the area of this guy right here. So I'm going to give to you that the radius is equal to 4 meters. I'm going to give to you that theta is equal to 1 radian. And I want to calculate the arc length, and I want to calculate the area of that sector. So now I'm just giving you numbers. I'm telling you that this is 4 meter radius circle. I'm going only 1 radian in terms of the angle there. So how do I find the arc length? Well, I just go back to my arc length formula, which we've already looked at right here. S is equal to r theta. You just always start with there. So the arc length from here up to here is equal to r times theta. Now the radius is given as 4, and the theta is given in radians, so we don't have to do any conversions. And so 4 times 1, when you put these guys in here, is equal to 4. Now what units should the distance be in? Well, the radius was given in terms of meters. The radian is like its own unit. It's really sort of dimensionless. It's its own invented unit. So since you have meters for the radius, it's going to be meters for the arc length. So the arc length is 4 meters. That means the curved distance from here all the way up to here would be 4 meters. All right. Next, let's take a look at the area. Now we're trying to find the area. Now there's 2 equations you can use for the area. Let's go ahead and use the first one here. 1/2 r squared theta. So 1/2 r squared theta. Now what is the radius? The radius is given in the problem as 4, so you have to square that, 4 squared. Theta is 1 radian, so we have everything in the correct units right here. And then we could say 1/2, what is 4? 4 times 4 is 16. And this is times 1, so you just have 16. And then the area, 16 divided by 2, is 8. Now, what unit are you going to have for the area? Well, we have 4 meters for the distance unit of the radius of the circle, so the area has to be in square meters. So it's going to be 8 square meters. Now, just to show you that it doesn't matter, let's go ahead and use, instead of this equation, let's use 1/2 r times s. The area of this circle can also be 1/2 r times s. And what is the radius? The radius is 4. And what is the arc length? Well, it wasn't given to us in the problem statement, but we actually calculated the arc length of this problem before, so you can put that in there. 4 times 4 is 16, and you can see the 16 divided by 2 is going to give you 8, and it gives you exactly the same number. So it surely doesn't matter which equation for the area you use, you are going to get the same answer each time. All right, let's do our very last problem. We're going to do the same sort of thing. I like to draw a little sketch of these all the time, even though it's the same exact sketch, because I want to make sure that I'm on the same page with myself and I don't get confused. So here I have some radius, this is some angle, this is some arc length, and this is some sector area. I just do a little sketch showing you what the variables are. Now for this next problem, I'm going to give you that the radius is 4 centimeters. The arc length is 12 centimeters, but we want to calculate what this radian measure is in terms of that central angle there, and also what is that area. So we're given kind of different variables here. So if I want to calculate theta, there's a lot of different ways to do it, but let's just go back to our equation for arc length. S is r theta. We can calculate theta using the arc length formula. So what we'll say is S is r theta, right? And what we'll do is then we'll just say that the arc length is given in the problem is 12 centimeters, and the radius is also given in centimeters, so we can put the 4 right here, and then we have a theta. So theta, 12 divided by 4, when you divide this guy over, and then that's going to be 3. And does it make sense? Well, the arc length is in centimeters, the radius is in centimeters, so these are compatible units. We don't have to convert anything. And so when we have these incompatible units, we know that the angle is going to come back in radians. So it works out to exactly 3 radians. Now, just for comparison, you know that pi is 3.14. So pi radians would be if you would go all the way around to the other side of the circle, right? So it's a little bit, so I've drawn it as a very small angle, but actually this angle is much closer to a half of a circle, a little bit less than a half of a circle. 3.14 radians would be exactly half of a circle. 2 pi radians would be all the way around the circle there. All right, last thing we want to do is we want to figure out what the area of this guy is. And again, we can use either one of these equations. Let's just use the first one, which is 1/2 r squared, 1/2 r squared theta. So 1/2, what is the radius? 4. 4 squared, what is the angle measure? The angle measure we calculated in the first part, which is 3. So we have a 3 right here. So we have, this is going to be 16, so it would be 1/2 times 16 times 3. This is going to be 8 times 3. And so the area is going to be 24. 24 what? Well, the radius was in centimeters. This was in radians. And so if we have centimeters, we're squaring it. We're going to get square centimeters. So we can put centimeters squared or square centimeters right here. 24 square centimeters. So it would be much easier if I just opened the problem up and said, oh, here's the equation for the arc length. Here's the equation for the sector of a circle. And, you know, bingo, bango, you just start solving your problems, right? That's great, and you could do it, of course, but you wouldn't know what you're doing. You wouldn't know where it came from. You certainly would not remember it a year or 2 from now. So I spent a little bit of time motivating and deriving where they come from. Actually, these equations, I mean, the area, sector area is something you use every now and then, so I can't really hang my hat too much on that one. But this arc length formula, we actually use it a lot in physics. I don't want to get into it now, but it's because when things rotate, like a tire, when it rotates, then we can say that the tire has a angular velocity. So we're not getting into that here. We're going to get into that very soon. But we can talk about how fast things rotate. And so we have to look at the distance the thing travels along its circumference, which is its arc length. And then we can also talk about how fast the angle is moving as well, which is its angular velocity. So the arc length formula is like a stepping stone to talking about angular velocity of rotating objects. So if you think about physics, any kind of machine that has a rotating element, you almost always end up using arc length and also some stuff we'll talk about in a minute, angular velocity. That's just how many radians per second the thing is rotating. All right, so we haven't gotten to rotating objects yet, but that's kind of like what we're building the foundation for. So some things I tell you, oh, not so important. This is actually not one of them. We use this quite a bit. And so I want to emphasize the fundamental definition of what the radian is so that you understand why it's a more natural unit, so that you understand how these things come about. So solve these yourself, make sure you understand the derivations. Follow me on to part 2. We'll continue to talk about radians, arc length, and sector area.